Speaker is Floris Bruynooghe, who is going to be speaking about build your microservices with ZeroMQ.
Hello. So yeah, I'm Floris. I've been writing Python for quite a while, and currently I'm working on Kobe.io, and this is it's a monitoring platform, and we've kind of designed the backend to be microservices in using ZeroMQ as well to communicate, etc. And this talk is a little bit based on that experience that we have from that, and I think it's a very good way of making a resilient backend. I think. Obviously, when we started this about a year ago, you know, we've learned along the way. We didn't do everything perfect either. You know, software kind of is a living thing, and that kind of works like that. So. Yeah, but I think this is I think it's a nice way, and often microservices tend to nowadays use HTTP with JSON, and I think it's nice to think about other ways of doing this. So, just a kind of an overview of what I will be covering, talking about today, is I'll kind of have it in two halves. The first one is sort of, I'll talk a bit about message passing, and I think how we kind of came from building monolithic applications to sort of towards microservices, and why that actually, to me at least, makes sense. And then on the second part, I'm going to discuss a little bit more about ZeroMQ, why it is a very, and it kind of ties in a bit, why it's a very nice way of using for communication. I'll then give a very quick worldwide tour of some, not really of very much details about ZeroMQ, but just some pointers and tips of what to look out for. And then also, I'll sort of discuss some patterns that we used that I think are useful for designing to use in your microservices when building this communication. There's not that much time, so I don't really go in an awful lot of background detail, so I assume you have sort of a high level overview of knowledge of why HTTP and the rest of how it works. And you sort of have a vague idea of what ZeroMQ is, at least. So, you know, it's sort of this socket library that sends messages around, but doesn't have a central message broker. So it's processes directly talk to each other usually. So I think message passing is actually a quite interesting. I think it is an essential kind of part. When we write like large code bases, etc., things usually end up being in separate. Things kind of compartmentalized, you know, like modules, packages, etc. And sometimes, like in monolithic applications, you end up having threading or something, or multiprocessing and that sort of thing. But things usually fall into sort of smaller tasks. And a common way, especially like when going to threading models, etc., is to because the way the operating systems kind of started implementing this, and when we were writing big monolithic applications, those were the tools we had available, so a lot of shared memory is sort of happening. But this observation from Joe Armstrong is like, well, you know, that is not how we work in the real world either. It's not really, if you want to communicate an ID, we talk to each other. We don't like open each other's brain and poke around in there directly. So message passing is kind of a very natural way of letting different tasks and different components work together. And it's also, it results, if you employ that in resilient, if you employ that more, then you actually end up in quite building resilient systems. So as we go sort of, Joe Armstrong, together with these other people, kind of realized this, and they were back in the late 80s, I think. They were asked to write some software for their work. And one of the, and you know, as any good software engineer, they went, well, yeah, that would be, we'll definitely write that software. But they ended up kind of writing a language first instead of actually the software. But what they did is because they designed the language around these smaller components, and they actually embraced this, like, let's make lots of little tasks and let's make them communicate with each other. So everything, the structure they set up was, if you can decompose your programs into all these smaller tasks and make them talk to each other, the task itself actually become quite small and a lot simpler to work on. And they did the communication they did via message passing. In this, they created, they made an actor implementation essentially, and they just became little loops of like, wait for a message. Then if you get a message, do something, and then maybe send some other messages, and then when you're done, just wait for the next message and process the next message. And this resulted in a very robust kind of language that was really good for building big and scalable systems. And the other important thing they did actually when they were creating Erlang was having all these hundreds and thousands of little tasks actually that they have. Is you have to sort of manage those, because if you have an error, you know, they may die. And they took sort of this attitude of let it die, sort of one of the mottos they have. And to work around that, they basically they have these special supervisor kind of supervision tasks that look after the other ones. And if one of the tasks dies, they just restart it in particular ways, etc. And to build like the massive big applications, they end up building these supervision trees, like with supervisors supervising other supervisors, and then maybe a combination of actual real tasks and supervisors. And that has proven to be like a very good way of writing software. It's just basically try and decompose it as far and as you can, and then communicate with each other. So in a way, I kind of think of Erlang as kind of an original kind of nano-services way of writing programs. But in the meantime, like since the 80s, the infrastructure around us has been improving as well. So while you know on a big mainframe it was easier to deploy one big application kind of thing, then you know it became easier to kind of have your own servers for your own project, and we kind of went to service-oriented architectures a little bit in between. You know, it was already smaller, still quite big to deploy, but then the infrastructure around us kept improving as well. We started getting cloud services for spinning up new virtual machines, etc. You just call an API call, you get a new virtual machine. So things kept scaling down, and this basically all because the infrastructure around to manage these things kind of came into place. So packaging and distributing your application to your infrastructure just became easier, and it allowed you to it allowed us to shrink our individual components. And this basically, like with containers, we actually we then managed to go from sort of a whole a single process per container kind of mapping, and that means basically you can now just have in your own application you just, because all of that work is being offloaded to the tooling around you, your application can just become smaller and smaller, and that's really nice. So, and I'm a big I think Kubernetes is a very, like the orchestration systems that we got, like Kubernetes is really nice, kind of takes that further, because it takes that property of the supervision trees that Erlang has, and it means that our microservices don't really have to worry anymore about logging or about dying. If they have an error, you just let it die, and Kubernetes will sort of ensure that it gets restarted and you get the right number of your containers keep running, and that allows us to shrink sort of our process, and we end up being easier to write our applications as whole processes or containers. And the other benefit of that is while Erlang is kind of these nano services and maybe this, I don't know, You could think of it as like the ultimate goal, but the other benefit is with containers, we completely isolate it, so we don't all have to write the same programming language. We can now write in Python, you know, a language that gives us looping syntax rather than something like bizarre from the 80s that doesn't do looping syntaxes. So that's kind of where this allows us to get to. So ZeroMQ then. ZeroMQ is a very, it's a kind of a socket library. So it's very well supported on many platforms. It's really stable, well tested. But it's essentially a socket library, but it gives nice properties, so you can send messages to each other, and you don't have a central broker, which is really nice to build kind of distributed architectures. And kind of one of the main benefits that I kind of compared to like HTTP with REST request is you get out of, with the problem with if you do this HTTP request is you actually have a very strict pattern. You do a request, you get a response. And if you end up building lots of microservices that do need to do this, what you're calling another microservice, and then you have to go and wait for the response. And if the and if you call services several layers deep, etc., you still have this very direct call graph of dependencies that all need to be there. And if you're not careful, you actually have like the same thing as a monolith, because it's essentially function calls, but instead of doing it in process, you now have an extra network layer that can go and fail as well, which, you know, networks do fail. So just like you can try and improve things with adding timeouts, etc., but it doesn't. You still have a quite restricted way of organizing things. So that's why I think like ZeroMQ brings kind of new possibilities in. ZeroMQ itself is like, it's a very quick kind of, what I think is good points of ZeroMQ is kind of, it keeps persistent connections, so it can do really low overhead communication. It's very good at like grouping packages if it needs to, but still keeping the latency very low. And it gives you reliable, so it delivers whole messages and it gives them always in order, etc. It transparently reconnects as well, so you don't have to worry about, oh, the service isn't there, I'm going to have to back off a little bit and try and reconnect in 3 seconds and then maybe in 5 seconds and all those sort of things. So I kind of like to think of it as like Python dev is like one of the sayings they have is like, oh, we read Knuth, so we as Python programmers don't have to, so they do that. And ZeroMQ is a bit like that, you know, they do the horrible, nasty networking stuff, talking with kernels and all the sorts of things that, all the stuff that can go wrong. And we just get this nice messaging syntax on top. And the other benefit is language agnostic, so you can just communicate. You don't care what your microservice is written in, but obviously that's the same as in HTTP. The last thing is kind of, it's got a very nice user level syntax, so it kind of does things asynchronously. So you just say, I want to deliver this, I want to send this message, and it just returns straight away. And it takes it away, and then it goes and has to deal with all the kernel drivers and the buffering and the network, etc. And you don't have to worry about that. You just receive and send atomic messages, and everything else happens sort of in the background, and it's much easier to write with. Saying that, there is some, you know, not everything is great. It is a bit lower level. So HTTP, because ZeroMQ is the transport, so HTTP is a little bit lower level. You have to actually design your own protocol, which you don't have to do with HTTP. With HTTP, you only have to worry about the payload. So, you know, JSON is a common format. You can still transfer JSON around in this, or you can use something else. We tend to use message pack. But the fact that your communication pattern of when do I send a message, when do I receive a message, is now your problem. So you have a little bit more work to do. And the other thing is, and in those communication, when these protocols, one of the good tricks is kind of to always, ZeroMQ messages are kind of divided up in frames, and to always kind of start with a version frame, so you can easily change your protocol just by selecting on the version kind of frame. The other kind of a little bit difficult thing sometimes in ZeroMQ is that you have no knowledge about connection, so you don't know if your peer is actually connected, because on the previous slide I said, you know, it handles this automatic reconnection for you in the background. It also means you don't know if the other side, if your peer is actually live, so you're just sending things. And that can be sometimes a little bit difficult, so, but that depends on your protocol. If you design your protocol kind of right way around, then you don't really have to worry about it. Sometimes you end up having to do hard beating to actually know your peer is there, and that is not very nice at all. So it's nicer to try and avoid that. So now I'm gonna go really quickly through the slides because I don't think there is enough time to go in as much depth as I would like. But just some pointers about things to look out for when using ZeroMQ is when there's always queues associated. So if you have two peers that talk to each other, you create a socket on each side. There's no central broker, but you do get queues, and they're just in memory on either side, so they're associated with the socket, and they don't tend to really explain in a nice consolidated way where when those queues get created and when they get destroyed. And that's sort of important because if there's messages in your queues when they get destroyed. So in general, they sort of get created when you're receiving connections. They get created when the peer first connects to you. When you're making outgoing connections, they sort of get created when you make the connection, even if there is no connection yet. But it's something to watch out for when the queues get created and get destroyed. The other thing about queues is that it gives you some sort of back pressure. So if the queue is full, depending on the socket type that you used in ZeroMQ, which I'll get to in a second, when the queue is full, either it will block or it will just silently drop your messages. That's okay. Your protocol can just take that into account, and that sort of gives you back pressure. So if you've got too many messages, you can decide to start. If the other peer isn't like consuming them fast enough, you can kind of block. In Python's bindings, you probably want to reconfigure that to not actually really block your application. And sometimes it doesn't really matter, but even if it doesn't really matter, if you actually really block, then you have no ID because you're just stuck somewhere in a C stack, in a C call, and not in Python world. So it's much nicer to just let it raise an exception, and then you can log saying, hey, my queues are full, and then you can still decide to block or do whatever, but at least you're in Python land. The other thing to look out for if you're starting is like every single tutorial pretty much starts with this request reply pattern. It's not a good pattern, not just because it's not what I said about HTTP, but also because there's weird internal states. I'm not going to go into that much detail, but they realized this well, and they're actually replacing this as well by some client-server thing. But that's not yet there. But basically, you can skip past the request reply, and dealer and router sockets are the ones. They're the workhorse of ZeroMQ. They're what you want to use. Very quickly, so the main difference between dealer and router, so you can connect them to many peers, so you can talk to many ones. The main difference is that the router can actually address a single of its peers. The downside, the flip side of that is that it needs to wait to receive a message, because only once it receives the message, it has the address of the peer to send the message to. Dealer is often used as the other side, and in that case, the only thing I would like to say for dealer is like, if you only connect to one peer, then you know who you're going to send things to. So that's often kind of used to connect a dealer to a single router socket. That's kind of a common way of doing that. PubSub is the other pattern that you probably want to use a lot. And it's basically just one-way communication. So essentially, you're broadcasting information to lots of subscribers. But it is a fire hose. So if the sending side will never kind of be bothered by clients not being able to keep up. But it does mean when clients when clients can't keep up, they won't, because the nature of ZeroMQ, you won't really know that the client won't detect that it has missed information, that it has missed data. So when you design protocols for that, you usually want to put in a counter. So you just put in a counter so that increments every time a message gets sent. And then the client at least can detect that, hey, I've missed something. And well, then it can try and decide what to do about having missed something. Yeah, so this is, I call it a service pattern. It's kind of, this is a common kind of microservice thing that we've been saying, I guess. And this is sort of, when you have a microservice that wants to manage a resource of some reason, of some sort, I find it really nice to kind of try and think of it as a state machine and actually write the states that this resource can be in, and then draw the connections, the state transitions that you can make. And once you have that state diagram, you can think of it. It simplifies things. So and then you can start thinking about what messages do I want to send to this to change from those states. And then when you're designing that protocol, the nice thing, the thing you want to look out for is you don't really want to design your protocol so that you send messages saying, hey, can you take this action for me, please? Because then you go back to the sort of request reply kind of style of things. Can you take this action for me? No, sorry, I was in the wrong state. Or yeah, sure, it was successful. It's much nicer to kind of make your message, your protocol that you make, to make it kind of level-based. So instead you just say like, hey, can you get this resource for me in this state? And depending on the resource you're managing, you may not even be bothered about waiting for the reply. You can just go and send that message and walk away from it. Obviously, to get the current state of the resource, you will have to wait for a reply. So you still have, sometimes you do have to do reply. But that's kind of a nice way of making your services kind of more resilient against all the weird things you can get in failure. The other one that I would like to point out is basically use PubSub. PubSub is great, and that's kind of consumers. It really decouples. Like if you can try and think of your problem that those two services want to talk, if you can somehow, even if you only have like one consumer for this publisher, if you can think of it as a PubSub problem, it becomes a lot more decoupled. And it will become more resilient. And it also simplifies your overall architecture, because if you make everything like a peer-to-peer connection where you actually have to know about the other sides, you end up often with this Death Star architecture of like all dependencies relying on each other, and like this using PubSub is really simplifies that sort of that situation. So that's if you can at all get away with using PubSub, it's usually a much nicer, a very good choice. And then lastly, I'd like to mention this sort of, because when going back to the beginning where I said, well, the infrastructure kind of takes place, so it takes over, and that's why we can write these smaller applications. And when I was talking about actors as well, every kind of service ends up doing the same thing. It's just waiting for messages. And then when it gets a message, you start to do something. So this is something that we kind of started, because the main loop of every application was kind of the same, so it's always the same boilerplate. So we started abstracting this away. And we came up with this stream abstraction, where you can basically just use a for loop. The for loop is the interesting part here that you want to look at. So you just process messages off your for loop, and then you do something with them. And if there's no message, the for loop, the iterator of the for loop will just block. Termination then becomes very simple. You just have this stream.send term. You hook that up to sig term or something like that, and when you want to terminate your application, send a signal, it just comes basically in as a message, but it's kind of hidden from you, and the for loop just exits and exits cleanly. The only other thing that extra does, that this stream kind of does, is it uses, here it's demonstrated with a context manager, and the only reason for that is that it also needs a context manager, is that you also have, if you get an exception in your message handling code or something, it allows the stream to sort of clean up itself, because it has some ZeroMQ sockets to open itself internally. But it's kind of it's a very nice abstraction that we kind of handled, and it's basically the core of pretty much every microservice that we have. It's publicly available currently in this ACT.zkit package, which is a little bit odd. ACT is kind of just our own personal kind of boilerplate removal kind of tool. It might not be applicable. I really would like to move the zkit package outside of it, because that's more of a generic usable thing. But yeah, it's a very nice way of removing the boilerplate in your services. And that's kind of this is kind of a repeat of like the main thing really. You don't have to like ZeroMQ if you don't like it. But if you think of your architecture, if you think of it as passing messages rather than as request reply, you start to think of your architecture different, and you end up building more resilient architectures. And yeah, look outside of the box of HTTP. You don't have to like ZeroMQ, but there are other options other than HTTP. So, yeah, thank you very much. That was a...
I think we have time for one question. Okay.
Yeah, thank you. That was awesome. I just have a question regarding one slide where you said like kind of don't use HTTP. So what's your take on something like REST API or WebSockets?
So REST is usually very request response based. So that comes with what I think is watch out. I mean it is useful sometimes. WebSockets kind of definitely work around this because you get a stream and then you have to implement your own protocols on top of that stream. So WebSockets are a nice way of communicating as well.
Okay. Maybe we can fit in one more. Okay, give a big hand to Floris.